Good day, everyone. Today we are going to discuss about Hesse configuration. So in geometry, the Hesse configuration introduced by Colin Maclaurin and studied by Hesse in 1844 is a configuration of 9 points and 12 lines with 3 points per line and 4 lines through each point. It can be realized in the complex projective plane as the set of inflection points of an elliptic curve, but it has no realization in the Euclidean plane. The Hesse configuration has the same incidence relations as the lines and points of the affine plane over the field of three elements. That is, the points of the Hesse configuration may be identified with ordered pairs of numbers modulo 3, and the lines of the configuration may correspondingly be identified with the triples of points x and y, satisfying a linear equation ax plus by equals c modulo 3. Alternatively, the points of the configuration may be identified by the squares of a tic-tac-toe board, and the lines may be identified with the lines and broken diagonals of the board. Each point belongs to 4 lines. In the tic-tac-toe interpretation of the configuration, 1 line is horizontal, 1 vertical, and 2 are diagonals or broken diagonals. Each line contains 3 points. So in the language of configurations, the Hesse configuration has the notation 9, 4, 1, 2, 3. The automorphism group of the Hesse configuration has order 216 and is known as the Hessian group. The Hesse configuration can be realized in the complex projective plane as the 9 inflection points of an elliptic curve and the 12 lines through triples of inflection points. If a given set of 9 points in the complex plane is the set of inflections of an elliptic curve C, it is also the set of inflections of every curve in a pencil of curves generated by C, and by the Hessian group of C, the Hesse pencil. The Hessian polyhedron is a representation of the Hesse configuration in the complex plane. So this is what Hessian polyhedron looks like. The Hesse configuration shares with the Mobius-Cantor configuration the property of having a complex realization but not being realizable by points and straight lines in the Euclidean plane. In the Hesse configuration, every 2 points are connected by a line of the configuration, the defining property of the Sylvester-Galai configurations, and therefore every line through 2 of its points contains a third point. But in the Euclidean plane, every finite set of points is either collinear or includes a pair of points whose line does not contain any other points of the set. This is the Sylvester-Galai theorem. Because the Hesse configuration disobeys the Sylvester-Galai theorem, it has no Euclidean realization. This example also shows that the Sylvester-Galai theorem cannot be generalized to the complex projective plane. However, in complex spaces, the Hesse configuration and all Sylvester-Galai configurations must lie within a two-dimensional flat subspace. So that's it for today's video. Hope to see you guys soon. Bye!